Okay, so in this video, we would be discussing about your chess engine. Okay, so first of all, I want to make a few clarifications. First of all, this video won't be containing very much code. Okay, because I don't want to scare you off by those things. So we will just be discussing the concepts behind the chess engine. Okay, the various techniques and those things. Okay. Okay, so these are the topics that we would be focusing on. Okay, so the most important of them is the search technique. Okay, so if you are building your chess engine for the first time, you should be focusing more on improving the search rather than improving any other parameters. Okay, so your engine should be able to search the important nodes first by doing good pruning. Okay, by following good pruning techniques. Okay, and should be able to determine which move to play. Okay, okay, so those are the more important things to follow rather than evaluation, board representation, and the other things that have been listed over here. Okay, so now we would start with board representation. Okay, so basically there are two ways: your bit boards and your square boards. Okay, so bit boards is the more popular one which is used. Okay, so what is it does is it represents your whole board uh, in form of 64 bits. Okay, and these 64 bits are for each of the pieces which are present on the board. Okay, and then we use bit manipulation on these bits to move those pieces on the board and capture and do the other stuff. Okay, so bitboards is the more popular one, and it is also comparatively faster, but it is not so much easier to visualize. So we our discussion in this video would be focusing only around your square boards. Okay, and in square boards we would be using a 10 into 12 square board. Okay, because this is the safest one out there. Okay, uh, sometimes it may happen that the piece may go off board and those things. So this square board provides uh, an easy level of safety implementation. So we would be focusing on this one. Okay, so this is how your 10 into 12 square board is gonna look like. Okay, so the rationale behind using a 10 into 12 instead of a 12 into 12 is that whenever we are moving any piece, we are essentially adding some value to the current position. Okay, so for example, if I want to move a rook. Okay, so if I want to move a rook, I can increment. Supposedly the rook is over here. Okay, so if I want to move a rook, I can incrementally add one value like this. If I want to reach supposedly a position 97 from 95. Okay, so this is gonna be in something like a loop. Okay, which is going to add a single value step by step to the current position. Okay, so we call these pieces or slider pieces. Okay, so rook, your queen. Okay, your bishop. Okay, I can't remember the rook, queen, bishop. These are going to be your slider pieces. Okay, so what slider pieces mean is that you can add a single value plus one to these pieces and loop this value to reach any position on the board. Okay, and then we have your non-slider pieces like your knight. Okay, so for moving a knight, you can just add a single value. Okay, so if I have to move from one place to other, supposedly I have to move from your 65 to your 44. Okay, then I have to subtract a fixed value minus 21. Okay, so what we would be doing is we would be maintaining an array corresponding to this particular night. Okay, which will list uh, the values that we can add or subtract to this night for moving the piece from one position to the other. Okay, so the rationale behind a 10 into 12 square board instead of a 12 into 12 square board is also something which is based around this night piece only. Okay, so supposedly if I'm standing over here at piece number 28. Okay, and if I make an illegal move, like your movement to a minus 21 move. Okay, so then where I will land is a 7 square. Okay, so this 7 square it is off board. Okay, that's why the computer would show us that this move is illegal and it would not permit us to move this thing. Okay, and supposedly if I make a move uh, like this. Okay, so I have moved two squares over here and one square down. So what I'm doing is that I'm subtracting minus 2 over here and a value of 10 over here. Okay, so wait a minute. So I'm a little bit sorry about this. What I'm doing is that I'm adding a value of 2 over here and subtracting a value of 10. Okay, so what the final position would be 28 plus 2 30 and then 20. Okay, so we would reach over here and this is also off board. Okay, so essentially what is happening is that a movement is getting wrapped around the board. Okay, so there it makes no sense to use a 12 into 12 board. Okay, because we would be essentially wrapping these pieces on the board and uh, the safety is ensured in this condition also. Okay, so next. Okay, so before moving on any further, I would assume that you know the basics of chess. Okay, so you should be knowing what an unpassant move is. Okay, those things and how exactly the pieces move. Okay, uh, so that is a kind of prerequisite to this. Okay, so now I would be defining a game state. Okay, so what exactly a game state is? It is a structure. Okay, which can represent a game at a particular moment in time. Okay, so supposedly I give you a square board. Okay, and a fixed set of pieces on the board. Okay, then our structure should be able to uniquely identify that state from the other state. Okay, so if I make any movement on the square board, then it would be an update to the game state. Okay, so what it is telling me, it is telling the current state of the game. Okay, so if we want to define the game state. Okay, so we should be able to uniquely represent your pieces. Okay, your pieces on the board, because your pieces and the side which is moving. Okay, so for defining the game state, we can take some idea from Venn representation. Okay, so this is your Fredwell Edward notation. Okay, so in this notation, what happens is that we have pieces represented in the form of strings. Okay, so these this starting substring. Okay, this is going to represent all the pieces which are present currently on the board. Okay, so we will be using the small cases with uh, we would be representing the black pieces with lowercase, and the white pieces with your uppercase. Okay, and the numbers that you are seeing on the screen, these numbers represent the empty squares. Okay, and these slashes, these represent the end of a particular row. Okay, so this would be representing a whole board. Okay, and then this W or B, W or B, wait one second. W or B, whatever it is over here, it would represent the side which is going to play, and then these things, these represent your casting permission. Okay, this represent the current active unpersowned square. Okay, so you can make an unpersowned capture on this square, and then we have uh, we have your half move clock over here. Okay, which essentially represents the number of half moves since the last capture of pawn, last capture, or a pawn advance. Okay, so this is basically used to determine if a draw can be claimed under the 50 move rule. Okay, so what the 50 move rule says is that if the opposition side doesn't make any capture, or any capture or a pawn advance during the last 50 moves, then the match is said to be a draw. Okay, and then after this we have your full move number. Okay, so these are the number of full moves. It starts at 1 and is incremented after the black pieces move. Okay, so these are the things that we can keep in our structure to uniquely represent against it. Okay, so what we have collected from this Venn representation is the side which is going to move. Okay, the number of half moves, the number of full moves, your castling permissions. Okay, the unpercent square, and piece on a square on the board. Okay, so what this means is that we have an array. Okay, an array of your 120 120 120 integers, which is telling me that at a current position which piece is present. Okay, so I can represent these pieces uniquely using some kind of enum value. Okay, and then I can place these pieces anywhere on these square board. Okay, so the other logical ideas that are worth noting is that we should have an idea of your king square. Okay, so uh, which square currently the king is positioned on. Okay, so this is going to be something like an array with two integers. Okay, so which will represent uh, the black kings and the white kings square respectively. Okay, so this is a quick way for checking whether we are currently in check or not. Okay, and the second thing, which is very much logical, is your material. Okay, so uh, if you have some knowledge about chess, then you must be knowing the worth of each of the pieces on the board. Okay, so like we have your rook, queen, king. Okay, and then knight. Okay, and then your bishop, and then finally your pawn. Okay, so a king is something worth around infinite. Okay, or we usually say it is worth around 10,000, 10K. Okay, it is worth around 10K. And okay, so this was not the king actually. Okay, so this is the king. Okay, this is the king. Okay, so a king is worth around 10K. A knight, it is worth around 300. Okay, and the queen is worth around 900. And the rook, it is worth around 500. Okay, and the bishop, it is also worth around of 300. Okay, and the pawn, it is worth around 100. Okay, so uh, these pieces define the material balance which is currently present on the board. Okay, so we would be using this table as a reference for checking how much material we have currently present over the board. Okay, so this is also an important part of your game state. Okay, and then finally we have an inverse mapping of each of the pieces with which square they are on. Okay, so what is this is going to be? It is going to be 12 into 10 array. Okay, so why 12 into 10? Because we have your six pieces over here. Okay, and then we have six pieces present on the board on both sides. Okay, so that justifies the rationale of 12. And then uh, then 10 because we can promote all the eight pawns to any of these remaining four pieces. Okay, so this array would represent all the square location of each of the piece which is present on your board. Okay, so we would be updating this structure as we will learn about your searches. Okay, so before we move any further, we would just stop to take a look at your min-max algo. Okay, so uh, this is the algorithm. Okay, so what Minimax does is that it gives us an a score which is the optimal score in the case of an optimal play. Okay, so if I have an optimal maximizing player and an optimal minimizing player, and then again an optimal maximizing player. Okay, so in this case the game the depth of the game is your 3. Okay, so we are searching to a depth of 3. Okay, so in this case it would look into all the moves that your minimizing player and the maximizing player can make at each of the depth. Okay, and then it would be returning us an optimal value which is achievable by the maximizing player, considering that both the players in the game are optimal maximizers and optimal minimizers. Okay, so what we do is that we start from the root. Okay, and then in this case the branching is only in two directions. Okay, so this is actually the most simple example in when we are developing a chess engine. The branching would not be in two directions only. Okay, so because at each position number of moves are more than two. Okay, so like in the starting position only the number of moves are, I think, more than 20. Okay, so the branching would be 20. Okay, and then the branches stemming on from the minimizing player, it would be also huge. Okay, so this is most simplest example. Okay, so when we start, uh, we would run this pseudocode, okay, and try to see how this is going to work for this particular game tree. Okay, so I have represented the game in the form of a game tree over here. Okay, so this is nothing but the representation of a recursion tree. Okay, as the computer would perceive it. Okay, so when we start from the node first, we would see if the player is a maximizing player or a minimizing player. Okay, so we are in this part. Okay, and then we would set the value to be minus infinity, and then we would run a loop for both of these child nodes. Okay, and then we would try to go into a recursion loop. Okay, we would call the minimax algo again on this node. Okay, so let me just start from the root node again. Okay, so supposedly I'm currently over here. Okay, so this is a maximizing player. Okay, so the value which it has currently, it is minus infinity. Okay, so the task of this player is to maximize the result which it receives from both of these nodes. Okay, so for each value of the node, okay, I'm going to call a recursion call. Okay, so uh, if it is moving in order from left to right, then the first call would be to node B. Okay, and then B would make a call to node D. Okay, so uh, we are moving from here then to over here. Okay, and then I have reached a depth of 0 because I'm subtracting the value of depth at each stage. Okay, so I have sorry, not here. I would reach a depth of 0 over here. Okay, so when I have reached the depth over here, then I this is a depth of 0. Okay, so I would be returning the value which or evaluation function would return at this current position. Okay, so these are nothing but your positions in the game. Okay, which are being which are being updated, and then they are being evaluated finally. Okay, so this node would return us a value of 3. Okay, so this value would be this value was initially minus infinity. This was also and this was plus infinity, and this was minus infinity. So this value this would be updated to your 3. Okay, so now we have a value of 3 over here, and now I'm at this depth, so I would make a call over here. Okay, so this node would return me a value of 5. Okay, so 5 is greater than 3, so the maximizing player would want this value instead of 3, so we have a 5 over here. Okay, so I have explored all of my nodes. Okay, so I have reached the end of this call, so I would be returning your maximum value. So I would return, okay, let me clear the screen. Okay, I will return a value of 5 over here. Okay, so I would return a value of 5. Okay, similarly, I would be exploring this part of a game tree. Okay, and then it would move to the left. Okay, so this has reached a depth of 0. It would evaluate the position over here, uh, and it would return the evaluation score, which is 6. Okay, then this part returns an evaluation score of 9. Okay, so 9 is greater than 6. Okay, so this value gets updated. Okay, and now I have explored both of my nodes, so I would be uh, returning this value back to the minimizing player. Okay, so now the minimizing player would receive both these values. Okay, so since this is a minimizing player, uh, it has currently a value of plus infinity. Okay, so what it would do is it would try to minimize both these values. Okay, so uh, when I had returned a value of 5, okay, it had stored a value of 5 over here, and then after these calls, it would receive a value of 9. Okay, but 5 is less than 9, so it would retain this value only. Okay, and this value would then be passed to your maximizing player. Okay, so I had a value of minus infinity initially, but now it would be updated to a value of 5. Okay, so similarly, I would have a recursive call over here. Then C would go to F, F would go to 1. Okay, then 1 would be returned over here. We have an initial value of minus infinity present here, and 2 would be returned. Okay, so firstly, minus infinity would be replaced by 1 and then by 2, since this is a maximizing player. Okay, and then we have a plus infinity over here. So this 2 would then be returned to the upper node. Okay, so this plus infinity would be replaced by 2. Okay, again we have a recursion call. Okay, it sees it goes over here 0. This value is initially minus infinity. Okay, where am I? This value is minus infinity. It would return a value of 0. Okay, this minus infinity would be updated by 0, and then it would check this position. Okay, so this is minus 1. Minus 1, we have reached a depth of 0, so minus 1 would be returned. Okay, so since minus 1 is smaller than 0, okay, so it would retain this value only, and then it would pass this value to the upper node 0 over here. Okay, so among 2 and 0, 0 is the lesser one, so 2 would be replaced by 0. Okay, and this minimizing player would pass this 0 again to the upper node. Okay, but since this is a maximizing player, okay, it has received both these values, so it would take the optimal value 5. Okay, and this is the value which the player can expect if he searches to a depth of 3. Okay, so if the game ends at this depth only, then 5 would be the final value that the maximizing player would be getting. Okay, so we have an improvement over your min-max algo, which is called your Negamax. Okay, so the Negamax is also simple. It is just that we consider both the players to be maximizing players in this case. Okay, so we don't have any minimizing player in case of Negamax. Okay, and we build our searches on the assumption uh, that the game is a zero sum game. Okay, so min max is also वैसे applicable on only zero sum games. Okay, so these all games are actually in reality zero sum. Okay, so if one player wins, the other player is going to lose. Okay, so what may be profitable for the maximizing player is actually a loss for the minimizing player. Okay, so the value that the player receives is always going to be a negative value. Okay, and then it is the other player is going to minimize or maximize on the negative value. Okay, so we return the value as negative is because the this these types of game are alternate games. Okay, so if we have a maximizing player playing, then we would have a minimizing player after that, and then the maximizing player. Okay, so the score which is beneficial for the maximizing player is actually a loss for the minimizing player. Okay, so we would just try to run this Negamax over this thing. Okay, so and see how this thing is going to work. Okay, so we have a value minus infinity over here. Okay, and then we have a call at B. Okay, so the value is again minus infinity. Okay, because this is also a maximizing player this time. Okay, the value is minus infinity over here also. Okay, so when we reach our final depth, we would be returning the color multiplied by the heuristic value of the node. Okay, so if supposedly the color of the maximizing player is 1, okay, and the minimizing player is minus 1, and the maximizing player is 1, okay, and then at this depth the color would be minus 1. Okay, so the value returned by this would be minus 3. Okay, and this would be minus 5. Okay, but we would be negating this value. Okay, so this is going to get converted in plus 3 and plus 5. Okay, and then we would be maximizing on these values. Okay, so the maximum value that I can receive over here, it is 5. Okay, so this minus infinity would be replaced by 5. Okay, and then I would be sending back this value to the upper node. Okay, so what is profitable for the maximizing player is actually loss for the minimizing player. Okay, so this we would be negating this value. Okay, so I will have a minus 5 over here. Okay, and similarly I would run this algorithm over here. Okay, so this seems quite obvious. This would come out to be 9, and this would send back a minus 9 over here. Okay, so now I have to maximize for minus 5 and minus 9. Okay, so minus 5 is the greater one. Okay, so this value would be retained, and this value would be passed to the upper node. Okay, and this value would become 5 over here. Okay, so similarly we would be running this algo on the right side also, and we would get a similar result which is 5. Okay, like we did in Minmax. Okay, so the code is reduced in Negamax. Okay, so we would be using Negamax also, uh, Negamax only in the future discussions. Okay, so so are we are done with our basic algos for the search. Okay, Minmax and Negamax. Okay, these algos would not be used in the chess engine, but they build the foundation for the other algorithms. Okay, so keeping those things aside, we would focus on the other important thing of uh, your game state. Okay, which is moves. Okay, so moves is actually different from game state, but it is an important part of the board representation, because moves moves are essentially updates to your game states. Okay, so we have your position. Okay, a current position on the board, and then we have updates. Okay, so I can have a list of updates. Okay, which I can run on the position, and these updates will allow me to change uh, this game state from one from point 1 to point 2. Okay, so I have an update present over here, supposedly u1. This will change 1 to 2. Okay, and if I have u2, this will change 1 to 3. Okay, because at a time there may be a large number of moves which are possible on the chessboard. Okay, so we would need some way to represent those moves. Okay, so that we can generate those moves and store them in a list. Okay, and then we can use the list to update your positions, like we have done over here. Like A is being updated to B and C. Okay, and then we would like to evaluate these position to a certain depth. Okay, so uh, these moves we would be also representing them using a structure. Okay, and then we would make a list of these moves, and we would pass uh, to your function. Okay, like make move or something of that kind. uh, Generate all moves. Okay, so that function would generate all moves and update the game state accordingly. Okay, so the obvious things which can distinguish one move from the other is your from and your to. Okay, and then we have your captured piece and the promoted piece. Okay, so why we haven't mentioned any of why we haven't mentioned the piece we would be moving is because it is quite obvious from the from and sorry, it is quite obvious from the from and two positions. Okay, that which piece we want to move. Okay, and then why captured piece is important. Why captured piece is important is because it would later help us in your move scoring. Okay, so and then we have a promoted piece. Okay, so if I have my pawn over here, okay, and I reach the end side. Okay, then this pawn can be promoted to some other piece. Okay, so a move is telling me that from where I'm moving, what piece I'm capturing, and what the pawn would later get promoted into. Okay, so these things these can be represented as bits or your structures. Okay, so I can have a separate structure for moves. Okay, where I write these things also. Okay, so some not very much obvious things are your unperformed captures. Okay, so if a move is unperformed, then the captured pawn is not on the same position as your two square. Okay, so if I do an unperformed capture, like a pawn is over here and the other one is here. Okay, so if I do an unperformed capture, the two piece is not very much obvious. Uh, the captured pawn is not on the same position as the final position that this pawn would be moving to. Okay, so I need to tell the computer that the move is an unpercent move. Okay, so it can update the game state accordingly and remove this pawn from the board. Okay, and the other thing which is important is your pawn start. Okay, so because if a move is a pawn start, then we have to set the unpercent square accordingly in your game state structure. Okay, and then we have some bits reserved for castling move. Okay, so if a move is castling, like if I am moving my king to this square. Okay, so it is not obvious that the rook has to be moved here in the updated game state. Okay, so that's why I have to tell the computer that this move is a castling move. Okay, so that it can update your game state accordingly. Okay, so for each of the piece which is present on the board, we'll make a move, and then we will store this move in an array with the corresponding scores of the move. Okay. Okay, so the main two types of uh, moves that we would be having would be capture moves, okay, and your quiet moves, okay, and then we would be having the scores accordingly to these moves. Okay, so what we have covered in this video is board representation, okay, and the game state, and these two algos, minmax and negamax, and representing the moves on the board. Okay, so in the next video I would be covering your alpha beta, the evaluation function, okay, and then few techniques which would help us to improve the search of the chess engine.